Now we will talk about the second experiment for motional EMF. The difference between this one and the first experiment is that our conducting bar, which is moving with constant velocity v in this uniform magnetic field into the page, is actually connected to a circuit which has a resistance R. Okay, so in that case, the induced EMF at the two ends will be basically converted into a current here. So remember that in the previous experiment, there was an induced EMF from top to bottom. There was a potential difference. And according to that, this is at a higher potential, this is at a lower potential. So there will be a current set up in the counterclockwise direction. Now, so let's try to reach this conclusion using Faraday's law directly. A conducting bar slides on two conducting rails, as we can see in the figure. The magnetic flux through the loop, well, what is this loop? It's the loop created by this conducting bar and the circuit, will be equal to the area multiplied with the magnetic field. Well, if this is at a distance x from the left side of the conducting loop, the magnetic flux will be phi b equals b l x. Lx is the area of this rectangular region. Okay, according to Faraday's law, the induced EMF will be equal to epsilon equals minus d phi b dt, the rate of change of magnetic flux, and that will be equal to minus d dt in the flux blx. Okay, since the magnetic field and the length are constants, so minus bl dx dt, and dx dt is precisely the speed of this conducting rail. So it's going to be equal to conducting bar, it's going to be equal to minus BLV. So we can see that the induced EMF will be equal to minus BLV. The current induced in the circuit will be equal to epsilon divided by R, and it's basically BLV divided by the resistance R. Okay, so this current is now an induced current. All right. So this is basically equivalent to the circuit. We have an induced EMF, BLV, which is basically giving us a positive potential on top, negative potential at the bottom. The current flows in the counterclockwise direction through this resistance R. The change in energy of the system during some time interval must be equal to the transfer of energy into the system by work. So if I look at the force acting on this wire, it is IL cross B. So the external agent has to apply a force to the right to set a zero acceleration. The IL cross B basically tells me that if the current is flowing in this direction, L cross B is pointing into the page, pointing to the left, because the L vector is pointing up. The right hand forefingers point towards the direction of the current, and we curl them to the towards the direction of the magnetic field. The thumb points to the left, so that's the direction of the magnetic force on this conductor. Therefore, we need to apply a force in order to balance this force, magnetic force, to get zero acceleration. Okay, so that the net force should be equal to zero. That's Newton's law, Newton's first law. So the power delivered by the applied force will be equal to the power is dE dt, energy, rate of change of energy. It is basically the work done by this force, small amount of work by this force dw dt, which is equal to F applied dx dt. Because F applied times dx is in the direction of the force, so we have the dot product giving us F applied times dx, cosine 0 is 1, and we have dx dt, which is the velocity, so it's F applied times v. So the power is, the applied force must be balancing the magnetic force ILB, so it's going to be IBL times V. And this is the power delivered to the circuit by the induced EMF, epsilon times I. This is epsilon times I, and epsilon is BVL, so it's going to be epsilon times I is epsilon over R. We have epsilon squared divided by R. Now what is this? This is basically the power consumed by the resistor. So our epsilon is equal to BVL, which is the current multiplied by the resistance R, because the potentials on these two sides should be the same. And so the current is BVL over R, which is the magnitude of the EMF, epsilon divided by R. So we see that the power input is equal to the rate at which energy is delivered to the resistor. So that's the rate at which energy is delivered to the resistor. It's consumed by the resistor. Okay, so we've talked about a second experiment for motional EMF, where we have a conductor moving with constant velocity v to the right in a uniform magnetic field. Now, since this is going to feel a magnetic force, IL cross B, the induced current on this circuit will be basically in the counterclockwise direction. As we talked about the motional EMF before, we have a positive potential here and negative potential here. The current flows in this direction. Well, there's another way to see that. If you look at this conducting loop and apply Faraday's law, the area of this loop is BL times X. The magnetic field is B, so BLX is the magnetic flux, and as this conductor moves to the right, the area is going to be increasing, right? So the induced EMF is minus the rate of change of magnetic flux, which is minus BL dx dt. Because B and L are constant, but X is increasing in time, the area is increasing, therefore the flux is increasing. So dx dt is the speed of this conductor V, so it's minus BLV. Therefore the induced EMF is BLV. And we know that the increasing flux here into the page has to be opposed by the current, the magnetic field created by the current, according to Lenz's law, which we will talk about later. So this current must be flowing in counterclockwise direction. The positive potential is on top, negative potential is at the bottom. This is the induced current. Now, at the same time, the change in energy of the system during some time interval must be equal to the transfer of energy into the system by work. And what is the work here? Well, this is moving at constant velocity, which means the acceleration is zero. Therefore, there must be an externally applied force, which is balancing this force IL cross B, which points to the left because the current is in this direction. L cross B into the page, the thumb points to the left for the right hand. And the power delivered by this applied force is dw dt. It's the small amount of work done by this force in a time interval dt. So it is F applied times dx dt, because the displacement and the force are in the same direction. We have the dot product having cosine 0, which is 1, so which is F applied times V. And F applied must be equal to ILB, because L and B are perpendicular here. We have sine 90. The magnitude is ILB. It's balancing this force, so this is ILB. Also, pointing to the right, ILB times V is the power. BVL is epsilon, induced EMF, epsilon times current. Current is epsilon over R, because the same potential appears here and here. Epsilon over R is the current. So we have epsilon square over R. That's the power consumed by the resistor. So the power input is equal to the rate at which energy is delivered to the resistor.